Hi, my name is Alan Baker. In 2020, I produced 4 videos on ZigBee networks, an introduction to them, and 3 on transmitting and receiving data using a ZigBee network. Because climate change is now prominent in the news, I've decided to include an extra video showing a software program capable of displaying humidity and temperature changes in bar graphs. The data displayed is derived from a humidity and temperature sensor. It shows the average, highest and lowest recordings in each case. You can retain batch results of recordings on specific dates. And because this program can also print out data, it can be used for a view of humidity and temperature change over a long period of time. I think this program would also make an interesting project for sixth form colleges and technical institutions should they wish to write a similar program. In part 1, I described the Arduino Uno development board and an equivalent development board. Both used the Arduino Integrated Development Environment, which is a graphics user interface. I checked with the control panel to see that the device software was functioning correctly. I then described the DHT11 and the DHT22 humidity and temperature sensors. I then linked up the sensors with the development board and through a sketch showed them working on a laptop screen printout. In part 2, I used the AT setup mode for the XPs in exactly the same way as shown in the ZigBee Network introduction video. I then demonstrated a video example of the XPs transmitting and receiving sensor data. In part 3, I demonstrated with a short video example of the miniaturized system in action with a laptop. I showed you how to program an Arduino Nano or an Arduino Nano clone. I then showed you how to build a portable miniaturized system. Finally, I demonstrated with a longer video example of the miniaturized system in action with a laptop. In part 4, I'll demonstrate with a short video example of an updated miniaturized system in action. This will include an updated screen display derived from an edited Arduino Nano sketch program that was used in the previous video. Because this is a long video, running into 1 hour and 35 minutes, I've decided to subdivide it into 9 parts, excluding the overview and the end section. In the description for the video, there will be also mouse clickable part sections. Viewers can therefore go to the parts of interest and possibly view the other parts at an alternative time. I've decided to stick to the version 2 XP since the version 3 XP is too expensive for the purpose of this video. An XP version 2 can be purchased for as little as £10 from eBay with the 5-volt adapter boards costing at reasonable prices in the UK from £4.50 to £12.50. Two years ago, when I described the miniaturized system, I pointed out that there were alternatives to using the 7805 5-volt regulator and two electrolytic capacitors. In order to take a 9-volt battery and reduce the power to 5 volts for it to be able to run the miniaturized system safely. Here are some voltage regulators available today. In the last video, I preferred the L7805 5-volt 3-terminal regulator power module. This was because there were only two inputs, which could be AC or DC, with a range of 7.5 volts to 20 volts, and two outputs, giving automatically a 5-volt output. This regulator, with a built-in heatsink, unlike the 7805 5-volt regulator, is much safer to use in educational establishments. Although the previous regulator circuit is still recognized throughout the world. However, it can burn your fingers if incorrectly installed. With the exception of the newly installed L7805 regulator power module, the hardware is identical to the previous video, with the XP, the DHT22 humidity and temperature sensor, and the Arduino Nano, this time the genuine article. Although, as I pointed out in my previous video, the cloned version was considerably cheaper, but required an additional CH340 or the CH341 USB software driver. In several of my videos, I spoke of using the CoolTerm app to display data. One further advantage is that you can record your data to a text file. I'll now connect the app to the XP coordinator. I'll then walk into the garden and switch on the miniaturized system. Because I'm filming in the UK autumn, I've placed the miniaturized system in a spaghetti holder to protect against any rain collecting on the DHT22 sensor. I would carry out this procedure in any damp conditions, but abandon the recording in heavy rain downpours. The recordings are done in pairs in case of any interference to the signal. Once the recordings are transmitted, the Arduino Nano has been programmed to go to sleep for 30 minutes. This time can be altered to suit the individual. Here are some other edited for time recordings. The labels under humidity, Celsius and Fahrenheit will turn into values when the program is run. There are two date and time picker components, two text boxes for the start time of the run and the end time of the run, and two combo boxes where the user enters AM or PM for the start time and AM or PM for the end time. The panel shows a color coding for the average, highest and lowest recorded values. There is also a temperature scale in the bottom right-hand corner. When the program has been run and the bar graphs are displayed, the user is able to locate and edit any file, print the results, and record the accumulated records of humidity and temperature for future use. You will need the print document component and print preview dialog component from the toolbox for the print routine. You will need the open file dialog component from the toolbox for the locate edit file routine. This recording was taken on the 24th of August in Swindon during the heatwave in the UK. The first file to look at is the CoolTerm capture file. Note the humidity Celsius and Fahrenheit recordings are duplicated again beneath the information as a separate record. This additional record starts with an asterisk that was written into the Arduino Nano sketch program. This asterisk is used to extract the record data. 2 copies of the CoolTerm capture text file can be made. One copy can be placed in the previous data folder. The other copy should be renamed as a raw text file. Let's look at the raw text file now from a recording that took place on the 24th of August. This text file is a combination of 2 capture text files that were recorded on the same day, with several frame numbers re-edited to provide numbering up to 40. With 4 records being generated each hour, this text file is equivalent to 9.5 hours recording. Now let's look at the star file. If we look at the C-stats file, the file has been further cleaned with the removal of the asterisk. This file could be saved for future use, but you should decide what to do, as it will be overwritten at the next program update. The D-stats file contains the average, highest and lowest values recorded of humidity, Celsius and Fahrenheit. The stats record file is for a long-term view of these statistics, which could be run for months or for years. The form designer code shows all components used in the program. Here you can see a panel has been placed over the form. Some C# programmers prefer to use the panel because it's easier for them to control events. These components are labels that will reflect the values for humidity, Celsius and Fahrenheit. Other components include labels for displaying text, 2 combo boxes, 2 datetime pickers and 2 text boxes. There are also print document, print preview dialog, buttons and open file dialog components. At the end of the video, I'll leave references where beginners can see how to build these components for themselves. Let's look at the forms file now. All the data will be held in one folder, so I've set up a directory path to it. These string lines will be used for reading file data. These are the initial values of the variables. Note that the lowest values carry a very high number. This is because I want the recordings to overwrite these values. They cannot start at 0. Also note, when I did assign the HA, CA and FA average totals a value of 0 little m, the compiler informed me that it was an unnecessary assignment. After some thought, I realized why the objection was made. To get the average value, a record count is essential. These are the stream readers and stream writers for the main part of the program. The CoolTerm capture text file has been renamed A_raw. It could carry any suitable name here. That's providing it has a TXT extension. After opening the text file to read, I create the star file to write to. When reading the raw file line by line, if I find an asterisk in position 0, I read all the data in that line and write to the star file. After all the data has been read, I close both files. I then open the star file for reading and create a stats file. This will be a clean file of data without the asterisk. The read file is subdivided into component strings. Humidity, Celsius and Fahrenheit values plus spaces are then written to the stats file. The humidity text file value is converted into a decimal. I then determine whether this value is the highest recorded or the lowest recorded. Finally, I need a grand total to calculate the average value later in the program. I follow the same routine for the Celsius values, and the Fahrenheit values. I count every record to determine the average values by dividing the grand totals by the record count. Finally, I close the read and write files. I now create the dstats file to contain the average, highest and lowest values of humidity, Celsius and Fahrenheit. The calculations for average values produces many decimal places. As I only want 2 decimal places, I use this formula. The other values, highest and lowest, are already set for 2 decimal places. I now convert all variables to strings. This time I use the same formula on all variables to play safe, because they're going to be displayed on the panel. I now link the appropriate label text to the string name. The label text will be overridden with the string value. From experimentation, I found that the generated bar graphs interpreting the data will be too small in appearance. So I needed to magnify this appearance, including the scale, by 5 to reflect an accurate reading. The display starts with low numbers at the top and high numbers at the bottom. So to pick a base flow point, mine was 780. You have to work backwards. For example, if you had a bar graph that was 500 points in height, you would have to subtract 500 from 780, giving a start point of 280 and ending at an end point of 780. After completing those calculations, I then needed to create a vertical scale line. For this, I needed a graphics object and an orange pen. I set the thickness of the line for the orange pen at 2 points. I then set up the object drawline. The value of 40 refers to the start position from the left of the panel. The value VHL1 refers to the starting position in height of the scale line. The next value of 40 refers to the end location of the scale line from the left of the panel. The value of 780 refers to the base value of the scale line. I now have to draw the notches. At point 120, the notch value would be an extra 10 points wide, as shown as 50 points between the VHL1 values. To get the notch values for 90, 60 and 30, in each case I multiplied the value by 5 as shown as NP. I then subtracted the value from 780 to get the VHL location position. Finally, I added an extra 10 points to the 40-point values between the VHL values to get the notch width of 50 points. No notch was required for the 0 point, as the base horizontal line for the scale would have overwritten it. Finally, I draw the horizontal scale line for the bar graphs. I'll then set up the brush to produce the rectangles. I'll start by producing the average value rectangles, then the highest value rectangles, and finally the lowest value rectangles. The values inside the brackets represent the colour of the brush, the start position from the left of the panel, the start position in height on the panel, the width of the paint, in each case 25 points, and finally the length of the rectangle, or what will become the bar graph. In each case, this final value must end at my selected baseline of 780. Now I draw the miniature scale guide to the bottom right of the panel. This time I magnify by 2 instead of 5. It's the same method as the previous scale method, including the notches. This time I'm able to draw the bottom notch. I also add labels to the panel to reflect the temperature ranges. For more information on drawing lines and rectangles, see reference 3 at the end of the video. Finally, to draw an end to this section, I close the dstats file. I'll now provide a demonstration of the locate edit file function. Because there's no room to display any file data here on the panel, selecting Open would have the same effect as Cancel. The locate edit file function requires two components to be dragged down from the toolbox: the Open File dialog and the button. Because there's nowhere to display a full file text contents on the panel, I've stripped back the coding of this function. Reference 2 at the end of the video will enable you to display a full text file on the screen. The coding for this function is very straightforward, requiring just 2 lines. Let's look at the Open File dialog properties now. and the events. I'll now provide a demonstration of the print function. You will need to drag down the print document component, the print preview dialog component, and the button from the toolbox. This is done in two stages. The first stage is to click on the print document component. This will take you into the coding. Enter the first line within the braces and the second line just below the second brace. Selecting the print button is the second stage. This is the best code that I researched from watching YouTube channels. See reference 8 at the end of the video. This code is very similar to the code produced by FoxLearn, reference 7. The difference between them is that this routine is written for printing the panel, while the FoxLearn routine is written for printing the form. Let's have a look at the properties and events of the print document and print preview dialog components. You must select Print Document, Print Page here. You must select Print Document here. This routine allows you to save screen captures to the Picture Screenshots file. You can save screenshots in PNG, JPEG and GIF files in the Screenshots folder. You can also print the screen capture. Due to memory constraints, my computer recording software would not allow both programs to run at the same time. I, however, have this example of a JPEG file that I saved. This is a comparison of a print that I created from running the program and a larger print of the same display achieved by the Snip and Sketch tool. I'll now provide a demonstration of the record function. The existing stats record file. Here's the updated file. For computer analysis of this file, the format of the date can be changed to reflect year, month and day. Put in the new values at customer format. Year must be in lowercase. Followed by a dash or forward slash. Month must be in uppercase, followed by a dash or forward slash. Day must be in lowercase. At format, you must select Custom. Selecting Short would reverse the date to day, month and year format. Now I'll run the program to see the changes in the stats record file. Here's the existing file. For a comparison, here's the same record with the new format update. If you wish, you can choose many other formats with a date and time picker. For this function, you will just need the button component on the panel. The C# coding is remarkably similar to what's been shown in the main part of the program. Here's the path to the file folder holding the data contained within a string. This is the string line containing the components that make up each line of the dstats file. Here's the first date-time picker containing the selected date format, which passes to the string std1 start date 1. Here's the text box one, which passes the start time to the string stt1. Here's the combo box one, which passes either AM or PM to the string stam_PM. The end timings are worked out in a similar manner. The routine requires a stream reader for the dstats file and a stream writer for the stats record file. This time, the stats record file will be file append text instead of file create text. String line 3 is used to extract the data from the read line. While not end of stream, the read line is split into component substrings. The write line is then set up, starting with the string spaces at SP09 and ending at SP22, including the start time at SP17 and end time at SP20. The write line will contain the average formulas of 2 decimal places for humidity, Celsius and Fahrenheit, along with the highest and lowest values of each one. In addition, it will contain the start date and time of the run and whether it was AM or PM, and also the end date and time of the run and whether it was AM or PM. Finally, the read and write files are closed. Note the date-time pickers have been returned to the original format. I test the program locally first before deciding whether or not to release it. Here is a normal release for Net 6.0 Windows. Deployment mode is framework dependent. The target runtime is portable. Here is another version of the program. Again, I test the program locally first before deciding whether or not to release it. again set for any CPU. The target framework is again Net 6.0 Windows. This time, the deployment mode is self-contained. The target runtime is Windows x64. This time I've selected the File Publish options of producing a single file. Now let's see if this program can run by itself. This was the earlier compiled version that I tested first before deciding to publish the program. In this section, I'll cover the whole update sketch program. I've commented throughout the sketch so experienced users can skip through the video and the 10 slides detailing the sketch. I'll show the video first, showing how to download the libraries, the compiling process, and finally uploading the compiled sketch to the Arduino Nano. The reason I've decided to output 2 records every half hour is 1, to conserve power for the Arduino Nano, and 2, to limit the possibility that one of the records might be corrupted due to radio interference. Before you compile the sketch, check that the Arduino GUI is configured for the Nano version. Under Tools, check against Board that the Arduino Nano is selected. Check against Processor that the 80 MHz 328P is selected for the genuine product. If you have a clone version, I found the old bootloader version was more suitable. Check your port again and select it, because another device connected to a different port might take precedence. Here's the sleep library to download. As you can see, I've already installed it. The Install tab is in grey. If it was white, I could then go ahead and install the library for the first time. Here's the DHT sensor library to install. This library has also been installed. The Install tab is in grey. Let's have a quick look at the sketch that I've pieced together. I'll cover the sketch in more detail with a PowerPoint presentation shortly. and now compile it. The compiler didn't like one word from the sleep library which it thought was misspelt. So I compiled it again. A clean result this time. Now I'll upload the sketch to the Arduino Nano. A clean upload. So the first thing to do is to download the sleep library as shown in the preceding video. The first count enables only 2 records to be outputted at a time before the Arduino goes to sleep. The next count, count 1, has been made into a long. This is because if an individual decides to replace my 9V to 5V voltage regulator with a permanent mains driven regulator down to 5V, then the program can be run for days or even months. The count 2 starts at 10. This indicates that it would take 10 seconds for the first record to be displayed, and it'll be doubled to 20 seconds by the time the second record has been displayed. Sleep is defined in the library and will be attached to power down mode and sleep delay in the sketch. Sleep time is an unsigned long and is used to determine the length of sleep in milliseconds. You now need to download the DHT sensor library as shown in the preceding video. The next line defines the pin that I'm going to output data from on the sensor device. I then define the sensor type, DHT type, DHT22. The DHT11 is commented out. The last line on this slide links the pin and sensor as part of a function. I then set up the bitrate for the Arduino Nano or the Allegro version. I've set a sleep time for 1,800,000 milliseconds, equivalent to 30 minutes. This part of the sketch is straightforward. I set up a delay for 2 seconds for the serial output to be ready. I then print a blank line followed by a line of dashes and a blank line following the dashed line. This provides spaces between the readings. The humidity and Celsius values are then passed to float H and float C. I'm using float values because I expect decimal values and not just whole numbers. Finally, I've added a formula to provide a Fahrenheit reading. This next part of the sketch is also straightforward. I've added a function that if any of the input values for humidity or Celsius are invalid, then those values are skipped and an error message is generated. The sketch then returns for the next input values. As you can see, this part of the sketch deals with printing data. I wait for 2 seconds for the output to get ready. I then print frame and its number. Then I print humidity, Celsius and Fahrenheit values in separate lines with a 1 second delay between them. Finally, I print a blank line. I now wait a second to allow the serial output to get ready. Then I print a blank line. I then print a 1-line record consisting of an asterisk, the humidity, Celsius and Fahrenheit values. If any of these values are below 100, then print a space in front of the value. If any of these values are below 10, then print a further space in front of the value. The Microsoft Studio Community Edition C# program will later read these values as a full record, so the positioning of these values is crucial for the program to work efficiently. In this slide, I wait a second for the serial output to be ready, then print a blank line. I then print a wake 4, followed by the value of count 2, which determines whether the Arduino Nano has been awake for 10 or 20 seconds. I then print seconds. Count records the number of records. Count 1 is adjustable for battery use, which is shown in the next slide. Count 2 simply adds 10 seconds each time, the time it takes to display a record. Finally, I add a delay for 1/10 of a second. I only want 2 records to be displayed every half hour. This value can be altered if you wish. Count is set back to 0. Count 2 is set back to 10. The amount of seconds it takes to display each record. Count 1 is set for 20, the number of frames or records, which you would expect from a low-cost battery. This should last between 4 and 4.5 hours, depending on the weather condition. The DH22's operating range is between 0 to 100 relative humidity. So if it gets wet from a rain shower, it will more than likely record 99 to 100% relative humidity. More expensive long-life batteries might last up to 30 frames. 28 frames is equivalent to 6.5 hours, while 30 frames is equivalent to 7 hours. So experiment first. You could also use 2 low-cost batteries for a longer operational period, but keep the CoolTerm app running while you change the batteries. If the set record limit has been reached, the next 5 lines provide the user ample time to change the batteries. This final slide shows that if 2 frames of records have been displayed and the set frame limit has not been reached, then the Arduino Nano is instructed to power down and go to sleep for 30 minutes. This section contains a circuit diagram and 6 photographs of the system, 5 of which are labelled. Finally, there is a parts list should you wish to build a similar system. I hope you found this video of some use. Goodbye for now.